This is part 2 of section 9-4, similar right triangles, starting with practice 5. We had just finished exercise 5. Practice 5 is similar in form. Find the value of k. Write your answer in simplified radical form. They're asking us to write our answer in simplified radical form, which probably means we're going to end up with a square root in our answer. So starting with this one, instead of using triangles and splitting it up and taking the time to do that, by now hopefully you can name these triangles in corresponding order. We do know that we have 3 right similar triangles because this is one large right triangle and an altitude is drawn from its right angle up to its opposite side, which creates the other 2. So with that said, let's go ahead and write a quick triangle similarity statement, starting with the largest one. Triangle BCA is similar to the medium-sized triangle. Remember, I'm going to use the same system I used before, short leg, long leg, hypotenuse. So CDA is similar to the smallest right triangle, BDC. Now we need to find the value of k. And since we've got 3 triangles, we really only need 2 of the 3. So to figure out which ones we're going to use, first of all, notice that k is a part of the smallest right triangle, and it's also part of the largest right triangle. So odds are we're going to use the smallest and largest. K is not used in this one at all. In fact, AC and CD don't even have measurements. So the mid-sized ones we're not going to use, so we'll use these 2. Largest to smallest, I'm going to go ahead and do it that way. Largest triangle to the smallest triangle when I set up my proportion. So starting over here, this is our largest, this is our smallest, so I'm going to start with BC is to its corresponding side in the smallest triangle, BD, as CA is to the length of DC, as, back over to the large triangle, the first and last, BA is to BC. Did the whole thing without even looking at the triangle. Just make sure that you have set this up correctly before you rely on it so much that way. Now we substitute in values for all of these lengths. BC is K to BD, which is 2, equals CA, which we don't know, so we'll just keep it CA, is to DC, which we also don't know, as BA, which is 10, is to BC, which is K again. Obviously, the middle ratio we'll not be using since we don't know either one of them. So let's bring these 2 together. We have k is to 2 as 10 is to k. This time we have extremes that are going to be multiplying together. So cross multiplying this way, we have k times k equals, cross multiply this way, 2 times 10. That gives us k squared equals 20. Get rid of the square, which means we have to take the square root on both sides to balance the equation, and then so k is equal to the square root of 20. Now don't take the calculator and use it. We're going to put it in simplified radical form. Factors of 20 are 1 times 20, which we're not going to use, 2 times 10, and 4 times 5. Of the factors left, 4 is the only perfect square factor. So we're going to factor this under the square root into 4 times 5 because 4 is a perfect square. So k is equal to, we'll split those up, the square root of 4 times the square root of 5. And so k is equal to, the square root of 4 is 2 times the square root of 5. 5 is not a perfect square, it doesn't have any perfect square factors. So k is 2 times the square root of 5 units long. Before doing the rest of the examples and practices in this lesson, make sure that you have studied the geometric mean altitude and leg theorems, because those will be crucial to you understanding what we're doing here. Example 6, rock climbing wall. To find the cost of installing a rock wall in your school gymnasium, you will need to find the height of the gym wall. So from here all the way up. We already know part of it. You use a cardboard square. So this is the student, and here's the cardboard square. And he sets the corner, or one of the vertices of the cardboard square, in front of it, where his nose is, basically. He looks up along that line of the cardboard, and he looks down until he can see the bottom, where the floor meets the wall, and up where the ceiling meets the wall. He may have to move forward or backwards to get into that position. Once he does that, it says he measures the vertical distance up to his eye line of sight, which is 5 feet, but he also measures how far out he had to walk to be able to see the top and bottom, which was 8.5 feet. So that's the information he has. Approximate to the nearest tenth of a foot, so we're going to approximate the height of the gym wall. Well, instead of using 3 right triangles and pulling them out and trying to figure out what goes with what, we're going to use the Geometric Mean Altitude Theorem. So by Geometric Mean Altitude Theorem, it says basically that if you have this situation with a right triangle and an altitude drawn where that gives you 2 more similar right triangles, then this altitude divides the hypotenuse into 2 segments, this one and this one, and that this altitude is the geometric mean. So since it's the geometric mean, we set up a proportion where 8.5 are in the means places, here and here. This is the geometric mean of both the segments that were created on the hypotenuse. So there's the geometric mean of this segment here and the other segment that was created by it, 5. So we skipped a bunch of steps to be able to set this up. So this is a pretty efficient theorem if you know how to use it. Okay, now we cross multiply. So 5 times W equals 8.5 times 8.5, or 8.5 squared. That gives us 5W. And when you square 8.5, you get, let's see, 72.25. Then to solve for W, divide both sides by 5, and W is about 14.5 feet, rounding to the nearest tenth of a foot, just like it said. Now, that's not our answer, however. That's just from here all the way up. We also need to add the 5 feet now using segment addition. So now we add 5 feet to the 14.5 feet here for W, and we get 19.5 feet tall. This is the wall of the gym. Example 7. Find the value of B. In this problem, we're not given anything about the altitude drawn in the large right triangle. So instead of using the geometric mean altitude theorem, notice we've got one of the legs of the big right triangle, or we're looking for one of the legs. So we're going to use in this one by the geometric mean leg theorem. Now there's 2 ways we can do this. We can do it one way when we've got one leg, and the other way when we've got the other leg. Since we have this leg, we're going to have to be mindful of the parts that we use in the proportion. So what this theorem says basically is that it creates a proportion where that leg of a large right triangle is the geometric mean, like that, of the hypotenuse of the largest triangle, which would be 6 plus 16, this whole hypotenuse. So the hypotenuse up here. And the other extreme that would go here is the segment of the hypotenuse that was created by the altitude that's closest to that leg. So since this one here, 16, is closest to this leg, we use 16. We don't use 6. If we had been talking about this leg in the big right triangle, then we'd use this segment. So that's the other case. Well, anyway, back to this case. Since this is the leg we're using, then it's the hypotenuse, which is 6 plus 16, and then where the other extreme is this part right here that's closest to this leg, 16. Now that you set that up, let's go ahead and simplify, cross multiply. 6 plus 16 is 22, is to b is to 16. Cross multiply, b times b equals 22 times 16. B times b is b squared. And then when you multiply 22 and 16, looks like we get 352. Now they didn't specify whether to find an approximation or an exact answer. Generally, when you're not talking about a real-world situation, which this is not, there's no indication that these are in feet or inches or meters or whatever. There's no context to the problem. It's not a real-life situation. Then most of the time we use the exact answer, which means we're going to have to probably use simplification of radicals. But we'll find both. Let's go ahead and get rid of the square by taking the square root of both sides. So we have b now is equal to the square root of 352. Now instead of getting into your calculator, which you could do, you could go in and find factors of 352 using the list function. I notice up here though, before we got 352, we had already had two factors, and notice that one of the factors is a perfect square, 16. So we kind of lucked out here. This doesn't always happen. So I'm going to re-factor those under the square root. That's 16 times 22. I'm just using these. Then I can split those up into the square root of 16 times the square root of 22. And then b is equal to, that's a perfect square. That gives us 4 times the square root of 22. Now 22 is not a perfect square, and 22 doesn't have any perfect square factors. 11 and 2 are not perfect squares. So we've got 4 times the square root of 22 units, and that's how big b is. Now, if you want to get an idea to see if it makes sense, this is 16. Look at the medium-sized right triangle. This is one of the legs. This is the other leg. This is the hypotenuse. Well, the hypotenuse is always longer than any one of the two legs. So since this is 16, this better be bigger than 16. So 4 times the square root of 22. Let's go back up to this step right here and see if what b is about or approximately equal to. So put in your calculator the square root of 352, and you do get about 18.8 if you round to the nearest tenths. So this is about 18.8, which makes sense that it's longer than 16. So this is a very reasonable answer. So there's the exact answer. This is the approximation. Example 8. Find the length of AC and the length of BD. AC is right here. BD is right here. This has several steps to it. Finding AC first, I'm going to come over here. To find AC, notice that we have a setup for Pythagorean theorem in this small right triangle here. If you'll just take a look at triangle ABC here, this right triangle ABC, we've got BC is the square root of 6, AB is the square root of 10. Well, as long as you have 2 of 3 sides of a right triangle, you can always find the third side using Pythagorean theorem, as you well have learned. So, by Pythagorean theorem, using triangle ABC, we have the hypotenuse, which is AB squared, equals the sum of the other two sides squared. So that's BC squared plus AC squared. Substituting in values for these, AB is the square root of 10 squared, equal BC is the square root of 6 squared, plus AC is what we're looking for, squared. Now I'm going to do the next 3 steps once, and then after this I would like for you to be able to see how that's worked so you can skip the next 3 steps as you start practicing, or you can put the steps in if you need to. But square root of 10 squared is the same as saying the square root of 10 times the square root of 10 equals the square root of 6 squared is the same as saying the square root of 6 times the square root of 6 plus AC squared. The square root of 10 times the square root of 10 is the same as saying the square root of 10 times 10. Just putting them together under one square root. Same thing here. Square root of 6 times 6 plus AC squared. The square root of 10 times 10 is the square root of 100 equals the square root of 6 times 6 is the square root of 36 plus AC squared. Now, the square root of 100 is 10 equals the square root of 36 is 6 plus AC squared. These 3 steps right here should be able to start going from here to here. Notice that you square the square root and look what happens. The square root and square disappear and you're left with 10. The square root and square disappear, you're left with 6. So these 3 steps can be eliminated if you understand this property on square roots and squares. Continuing the problem, we subtract 6 from both sides and we get 4 equals AC squared. Take the square root of both sides to get rid of the square, and AC is equal to 2. So we found AC. So I'm going to put 2 over here. I'm going to put it in parentheses showing that we found it later on. Now I'm going to come up here and we're going to start looking for BD. Now BD, we need to do one thing first before we actually find it. First of all, we need to find AD. We'll write number 1. Find AD first by geometric mean leg theorem. So, now we know AC is 2, but we don't know how long this one is. So we need to use one of the theorems that we've talked about that deals with the 3 right triangles that are similar. So using the geometric mean leg theorem, using the leg of the right triangle that we know, which is the square root of 10, this one right here, we can say, okay, that AB is the geometric mean. So I write AB here in my proportion, and I write it here in the means places. And then in the extremes places, this is the geometric mean of the entire hypotenuse, AD, and the other extreme would be the segment of the hypotenuse that was created by the altitude that's closest to the leg that we were given. This is the leg we were given, AB. So this right here, AC, goes right here. So substituting in those values, we have AD, which is really, let's go ahead and cut that up into AC plus CD, is to AB as AB is to AC. Now once we've done that, now let's substitute in the numerical values. AC is 2 over AB, which is the square root of 10, equals AB, which is again the square root of 10, over AC, which is 2. Okay, oh, sorry, this was AC plus CD. This would be AC 2 plus CD, because that's what we're looking for. We have to find CD. Okay. So then, let's put that together. We cross multiply. When we cross and multiply this way, we get 2 times 2 plus CD equals, cross multiply this way, the square root of 10 times the square root of 10. Okay, well, this is using the distributive property. We have 4 plus 2CD equals square root of 10 times square root of 10 is the square root of 10 times 10, which is the square root of 100. And then simplifying further, this would be 2CD, I'm just moving these around, plus 4 equals the square root of 100 is 10. Now you've just got a two-step equation, linear equation. So subtract 4 from both sides. 2CD equals 6, and then divide both sides by 2, and CD is equal to 3. Now that we know what CD is, we need it. I'm going to put it over here, put it in parentheses. We need that now to do our second step to finding BD, is literally finding BD. We're going to find it by, again, the geometric leg theorem. Geometric mean leg theorem. One more time. So to do this time, BD is going to be what we're looking for, and it's the leg that we're interested in. So that's how we're going to use the last time we used this leg right over here. This time we're using this leg. So that is the geometric mean. So BD goes in the means places of the hypotenuse, which was this whole hypotenuse here, which would be AC plus CD, which we've already determined, which is 2 plus 3. I'm going to go ahead and write it in here, 2 plus 3. To the segment of the hypotenuse that's closest to this leg now. It's not this one like before, it's this one, CD. And then we substitute in those values. That would be 5 is to BD, as BD is to CD. And CD was 3. That's why we had to find it a while ago. Cross multiplying this way, we have BD times BD equals 5 times 3. Multiplying, we get BD squared equals 15. Then taking the square root of both sides to get just BD, since we have BD squared, we have BD is equal to the square root of 15. Now 15 seems like it should simplify or do something, but it doesn't. 15 is not a perfect square, and 15 doesn't have any perfect square factors. 3 is not a perfect square factor, 5 is not a perfect square factor, and we don't use 1 in 15, so we're done. This is it. This is the square root of 15 is BD. So the answers to our problem, let's go ahead and write it here. BD is the square root of 15 units long. So our first answer, of course, was AC, 2, and our second answer was BD, which is the square root of 15. Our last problem, example 9, is about a doorstop. You are designing a doorstop that you want to be 2 inches tall. Other information is given in the diagram. How long is the base length B in inches? Well, I guess this represents the door jamb of the door, but this is the door stop. It's just a right triangle, a large right triangle, and they've got the height of it, so therefore we've got 3 right similar triangles once again. Now we're going to try to use one of our theorems here. I'm going to take a look. We've got the altitude, which probably or most likely will mean we're going to use the geometric mean altitude theorem instead of one of the leg theorems, since we have the altitude. So let's see if that'll work. By the geometric mean altitude theorem. Remember, it says that the altitude is the geometric mean, so I'm going to put it in the means places, here and here. Okay, and then I'm going to go ahead and do this so you can see how we did it. And then the extremes, that's the geometric mean of the entire hypotenuse, or both sections of it. So this would be up here 1, and down here would be B minus 1. Because remember, it's this right here. This is the geometric mean of this and this. Well, this right here is the whole thing B minus 1. That gives us this. This is B minus 1. So now we have this proportion to solve. Cross multiplying, we get 1 times B minus 1 equals 2 times 2. Using the distributive property, we still get B minus 1 equals 4, and then b minus 1, add 1 to both sides, and b is 5. So b must be 5. This hypotenuse right here must be 5 for this doorstop to work.